Alright, welcome folks. It's evening here in the Stats Bunker, and we're here to talk a little bit more about central tendency. So, today's topic, we will be talking about the mean, something that all of you should be familiar with from previous classes, but you may have heard it called the average. We call it the statistical mean for reasons that aren't interesting, but that's what we call it. So, again, the mean is the most commonly used measure of central tendency. Remember, the point of central tendency is to boil down a data set into one number that kind of describes the center of that data set, the most representative number that you can get. The mean is the one that we tend to use whenever possible. Again, the mean is calculated in a way that we all should be familiar with. We add up all the scores in the data set and we divide them by the number of scores. So for example, if I went to a bookstore and I kept my receipts and conveniently they all were round numbers, I might say, okay, what's the average amount I'm spending when I go to this place? I add up all the dollar amounts. They equal $160 divided by 4 trips. On average, I'm spending $40 a trip. That's a way of boiling that data set down to one number that kind of represents what my normal expenditure might be, what the average amount is. So the mean or the average is $40. As you should remember from the introduction piece of this module, we've talked about the formula for the mean, but just to recap, we're seeing these symbols for the first time in a lecture at least. So to recap, M is the symbol for a sample mean. Some places they represent it as an X with a bar over the top, but we don't do that here. Sigma is the capital Greek letter sigma, and again it means add up whatever's in front of this sigma here. X is all of the scores on whatever variable we're looking at. X is just the generic letter we attach to mean variables. So sigma X means add up all the scores on the variable X. Add up all the scores you have, divide it by this other very common score, N. So N is the number of scores that you have in the distribution. So let's see what this looks like with another data set. Let's say that we're looking to measure aggression in a study. And aggression is hard to measure directly because even if you can do it practically, there's a lot of ethical issues with it. So we have people do things like give opponents blast of static in a competitive game. So let's say they did that. We had 10 people do that. Notice, by the way, we're already using our N here, our symbols. Now let's say we measured the amount of decibels they chose to give to their opponent. The idea is the louder the sound they're choosing, the more aggressive they're being. So here are our 10 individual scores. We can pick out some general tendencies there, but if we want to boil it down to one number, the mean is a good way to go. Here's that formula again. Sample mean equals the sum of all the x's divided by the number of scores. If we add up all 10 of these scores, they add up to 845 decibels. We divide by 10, nice and easy. The mean or the average is 84.5 decibels. We've boiled that 10 score data set down into one number that summarizes what's happening in that data set. So here's a little bit of a look forward. And calculating the mean is pretty basic stuff. The mean is going to play a crucial role in a lot of things we're going to do later on in the session, but it's going to play an especially meaningful role in setting up our next set of descriptive statistics, our next module called variability. So variability is all about how much scores spread or differ from one another. How much do they tend to differ by? Usually the standard of comparison we use is how far away from the mean are the scores. Our score is pretty close to the mean, they don't differ much at all. Our score is relatively far away from the mean where it's pretty routine for them to be, several points away from that mean. That's the idea of variability. So here's the thing. The most basic form of variability is something you've almost certainly calculated before. So it's called deviation. And a deviation is just how far away each score is from the average score. Now here's an example. You get an exam back and your instructor tells you what the average was on the test for the entire class, and you have your own score in front of you. Mentally, just about everybody is calculating how far away from average are they. Are they above or below average? How many points above or below average are they? So again, that's a deviation score. I'm 5 points above average. Oh, I'm 8 points below average. How far away is your individual score from the average? So here we see another little formula. Notice we see our symbols repeated. X means the individual score on that variable X, and M, of course, is the mean of that sample. And you just subtract the mean from the individual score and you get your deviation. So here's the thing. Deviations work just fine for individual scores. They're a good way for thinking about your own test scores and that sort of thing, anytime you want to compare yourself to an average. They're really, really bad for entire distributions. The reason why is that the sum of, there's our sigma again, the sum of deviations in a sample always equals 0. Why is that the case? pause and think about it. The reason why is that the mean works like a balancing point. For every point one person is above average, somebody else has to be a point below average. So when you add up all the deviation scores, essentially you're taking all the points that people are above average, and you're subtracting all the points they are below average, and that's always going to cancel out. It's always going to equal 0. The reason why we're mentioning this now is this is going to be a really important part of our thinking about variability in that next module. So again, tuck this away, think about how these two things are related, and we will solve this problem a little bit later on in variability. So again, this is a point of emphasis. We're stopping to talk about this because it's really important. So the mean, again, is a key aspect to starting to model variability. This is a key dimension of the distributions of our variables. It's sort of how far spread apart are they horizontally. Distributions with exactly the same average score can have completely different levels of variability. So we need that added piece of information in addition to things like the mean to describe our distribution. And again, we measure variability generally by how far away our scores from the mean. That's not quite enough because if we add up all those deviation scores, they will always cancel each other out. So back to the mean. In addition to using the mean as a basis for variability, we also use it as a basis for estimating future measurements. If we have an average score, that's our best estimate for scores that we haven't gathered yet. For example, nobody's taken the first test in this class yet, or at least you shouldn't have. If you did, you're late. So nobody's taken the test in this class yet. If I wanted to estimate how I would expect the class to do, the average score in prior classes would be the best estimate that I have. Will this class be exactly on that average? Probably not. Maybe a little over, maybe a little under, but over time it'll wind up being really close on average. So we expect future scores to equal the average of the data we've already got. It's not going to be perfect. It's an imperfect process, but on average, it's the best information that we've got. So again, sometimes it'll be off by a little. Often it'll be off by a little. Sometimes it'll be off by quite a bit. Once in a while, it'll be just about spot on, but it's the best information that we have. Here's another important aspect of using the mean. Remember the difference between our sample and our population that we talked about? Remember also, anytime samples and populations come up, your ears should perk up. This is important stuff, a big part of what we're doing. M represents a sample mean, the mean of a sample. It's a statistic. Here we see this little Greek letter, looks like kind of a funky U. That is a mu. It's not like the Pokemon, it's just a Greek letter. And that represents the mean of a population. We'll see pretty consistently standard English letters used for sample statistics and Greek letters used for population parameters. Anyway, just like we've talked about every time we've talked about samples and populations, we always want to understand the parameters, the characteristics of those populations. So usually what we actually want to know is mu, but usually the best information we can get is the mean of a sample taken from that population. So mu is the very best predictor of scores in the population. It's the data that we want. It's what we really want to know. Usually it's impossible to actually figure out mu. So we use m as an estimate for it. Here's the thing. We know that samples are imperfect. They're not going to be exactly the same as our population. The mean of our sample is probably not exactly the same as the mean of our population. And it's possible that it's off by quite a bit. On average, it's going to be a pretty good estimate, but individually, there can be a lot of room for fluctuation. Here's how the sample mean will get closer and closer to the population mean. First, measure more people in your sample. Second, measure more samples and average those samples all together. Both of these involve get more data, measure more people. So the more people you have in your study, the closer and closer your sample mean will get to the mean of the population it's being drawn from. The more accurate it will become as you measure more and more people. That's going to matter for some more advanced stuff we'll talk about a little bit later on. But for now, measure more people, your sample means become more accurate for what we want them to do, which is estimate the population mean. This brings us to, again, a point of emphasis that's also for future service. That means it's important right now, and it's also going to be really important later on. The mean is the first time we've used a statistic, something from a sample, to estimate or to get information about a parameter, what we actually want to know. Again, it's called mu. This is the essential thing that we're trying to do in most research. We're trying to leverage information that we get from small groups of people, samples, to draw conclusions about massive groups of people. these populations with millions or billions of people in them, using the characteristics of a sample to try to estimate parameters of a population and the uncertainty that goes with that, the fact that it's probably going to be at least a little off. That's a crucial part of the logic behind hypothesis testing and how they're run. So always pay attention to when we're connecting samples to populations. It's really important. That's the end for the mean. We're going to come back and talk about our second measure of central tendency, the median. See you there.